Hello, thank you for joining us for the National Grid Spring Zero Net Energy Forum focusing on design. This session is sponsored by National Grid. I'm Connie Empress, Communications Manager here at New Buildings Institute. Before we begin, I have a couple of housekeeping things to tell you about. First, you are muted and we cannot hear you. This helps keep the background noise down so that everyone can better hear the speakers. I want to direct you to the dashboard that you should be able to see on the right-hand side of your screen. If you are having technical difficulties and cannot see the slides or hear our speakers, you can use this question pane in the dashboard to let us know, and we will help you as we go. We will take a few questions at the end of the presentation. Please ask questions in the same question pane. Please take a couple minutes to answer the survey that will pop up after the session. If you are seeking AIA credits, this is where you will enter your AIA number for credit. This session is being recorded. All registrants will receive an email tomorrow with links to the recording and slides for the session, and attendees will receive a certificate of participation in the same follow-up email. On your screen, you should be able to see the AIA approved learning objectives for today's session. Kicking off today's presentation is Mona Chandra. Mona leads the Commercial and Industrial Strategy team for the Rhode Island Program Strategy Policy and Evaluation Group at National Grid. She is responsible for program strategy and design of multiple energy efficiency programs and solutions. Over to you, Mona.
Thank you, Connie. Thank you all for joining our Rhode Island Zero Energy Forum on design. Like Connie mentioned, I'm Mona Chandra with National Grid, and I focus specifically on zero energy buildings. And before we get into the agenda, I just wanted to mention we have another upcoming webinar on policy. It's on June 2nd, so I encourage you to register for the event. We have some really exciting speakers. We have the Office of Energy Resources. We have the Rhode Island Builders Association, as well as examples from City of Cambridge, as well as the City of Newton for this webinar. The next slide. All right, so just a quick overview on the agenda. We have Laura Redormer, my colleague at National Grid, who will be giving us a quick overview on National Grid's pilot programs on zero net energy buildings. And then we have Adam Parker and Brett Webster with Rocky Mountain Institute, who will be speaking about the retrofit, zero energy retrofit for multifamily housing. And then we have Meredith Ebom, who will be presenting on ZNE buildings, saving money from the start. This is a recently completed study. And Meredith is with the Building Environmental Prop Plus group. We also have a case study. We have Jacob Knowles and Tony Tatone, who will be presenting on the Bristol Community College in Massachusetts. And Jacob and Tony are with BR+A Consulting Engineers. And with that, I'm going to hand it over to Laura Redormer to give us an overview about the National Grid program.
Great, thank you, Mona. And it's really exciting to see the great turnout today. The participation of over 250 participants is exactly what we're striving to accomplish with the zero net energy pilots in Rhode Island. And the goals of these pilots are really focused on creating awareness, increasing local technical capabilities, and also serving as a catalyst for market transformation. And as a utility, National Grid is not only interested in the energy efficiency of the zero net energy projects, but also the opportunity to create projects to inform rate decisions, as well as policy decisions that will further accelerate what we're all trying to do in the zero net energy construction, new construction, and major renovation market. The Rhode Island Energy Zero Net Energy pilots are offering enhanced incentives, including additional design assistance, energy modeling, on-site inspections and testing, and financial incentives. And the pilots include in-depth conversations with our technical team and helping with projects to achieve the higher energy efficiency and really getting to that net zero goal. The image that you see here is an exciting advancement that we have, and it's a website that we'll be presenting on the National Grid website, and it'll be a place where you'll be able to find resources, case studies, and upcoming events. And we will have that for both the residential and the commercial markets. Next slide, please. The Zero Net Energy pilot, a couple of highlights on the residential side. We started out the pilot with a very small number of Zero Net Energy projects in Rhode Island. And through the course of ongoing trainings and on-site education and working with many industry partners, we now have a pipeline of over 100 projects in Rhode Island, which is really exciting. And that was as of the end of 2019. And we really got there through workforce development, presenting case studies, tours, working with our partners in order to help to advance these projects. And what we really believe is that it's the trainings that are going to help the up and coming builders and building associates to develop these projects. We would like to call your attention to the contact information here in case people want to participate in the Rhode Island Zero Net Energy pilots. So the phone number for residential, and then the email address for Denise Rouleau for commercial. And we look forward to your participation in our program. And I'd like to pass it off to Adam Parker and Brett Webster with Rocky Mountain Institute.
Thanks, Laura. Adam Parker, Rocky Mountain. Brett and I are going to be presenting on net zero retrofits, 100% or close net zero retrofits in existing buildings. Before we start, we want to put the first poll question up for today. Please take a look at this and notice that we're talking about retrofit, net zero retrofits in buildings, not necessarily new construction. So please pick your number one barrier to this proliferating.
Well, Adam, it looks like upfront costs is winning by a landslide. Well,
that's very, very sound judgment on the part of the group assembled today. Let's talk about let's get into that. And if you could go back to, there you go. Next slide, please. We're going to start with the retrofit problem, and the retrofit problem in two senses. The first sense is that if we are to achieve the climate change goals that we need to achieve as a society, which is approximately a 50% reduction economy worldwide by 2030 and a further 50% or at least close by 2050, then we're going to have to take on existing buildings as well as new buildings. Now, I know a lot of people assembled here are focusing on new buildings, and getting it done right is absolutely essential, which this group knows perfectly well. But some high percentage of buildings, I've heard different numbers, that exist today will be here in 2050, and we're going to have to take 90% of the carbon emissions and energy use out of those buildings by then as well. And that is a daunting challenge. The other part of the retrofit challenge is that it's so hard to simply to do in addition to the cost. Next slide, please. We draw an analogy to the cell phone business, and you can see from both the quality and design of the graphic, not to mention the unbelievable handset on the right side of the screen, that this dates back to the early days of the industry. Imagine if you're a cell phone customer, you walk into a store and you say, "I'd like a phone," and they go, "Okay, that's fine, that'll be $1,000. And then they say, "Well, what are you going to do with that phone?" And you say, "Well, I want to talk to people and I want to send texts." They say, "Oh, you're going to need to negotiate a contract with base stations and cell towers." Oh, and after you do that, you're going to have to pick your frequencies, and you're going to have to buy time on those frequencies as well. And you can see where this is going. It creates an incredible burden for the consumer. The consumer just wants to say, "I want cell service, and I want you to integrate all the details, and I will pay you a fair price on a monthly basis, including financing my phone for 2 or 3 years, and that's the package I want, and I demand great performance." Well, we need to see that in retrofit. And if you go to the next slide, we can talk about the Energy Sprong model, which is a model some of you may have heard about, which originated in the Netherlands and is spreading fairly quickly through Europe and is making some inroads in the United States. Rocky Mountain Institute is one of the allies working on developing the Energy Sprong model in the United States. You can break it into two pieces, as you can see on the screen. The first is a design and construction element, which I will leave to Brett, since that's the bulk of the presentation today, but how we achieve dramatically reduced costs for the rebates, for the retrofits over time, as well as a simplified process for the building owner and for the tenants in terms of a quick and non-intrusive installation process. But the other aspects of it relate to contracts and finance, an energy plan that deals with the split incentive problem, where energy costs or retrofit costs are paid by the building owner, but a lot of the energy costs may be paid by the tenants. We have a contractual method that solves that problem. It also includes performance guarantees, so that the performance is part of the contract, not simply something that is aspired to, but it is part of the contract, and it is enforceable for a 30-year term on the parties who engage in it, with appropriate financial products put in place to guarantee that. So I'm going to turn it over to Brett now to get into the physical guts of the model and its implementation, and I'll come back at the end to at least tease you on how a portfolio owner can think about taking this on in a broad way and solving this problem over time.
Great, thanks so much, Adam. Yeah, so drawing on the Energy Sprong model, I'm going to talk through some of the details of our first project in the Realize initiative, trying to adapt and implement this type of retrofit solution in the US. So our first pilot is on the Eva White apartment building in Boston, Massachusetts. It's a 7-story building with the first floor an open breezeway. Affordable housing, currently undergoing a RAD conversion and transfer of ownership from the Boston Housing Authority to Wynn Companies and the Castle Square Tenant Organization. Wynn Companies has been a great ally in this project, in working with us to sort through the transformation that it takes to deliver one of these industrialized retrofits, and what a departure that is from sort of the business as usual approach. The Eva White building was selected based on a typology study that we did on multifamily buildings that were 30+ units across the Northeast. And the idea in selecting the Eva White building is that the solution developed here could be widely applied to a similar set of buildings across the region in a similar climate. The baseline conditions of the Eva White building are typical, I think, of a lot of older mid-rise buildings: single pane windows, uninsulated CMU walls with a brick veneer, minimal roof insulation. You can see on the photo here some through the window AC units that are tenant owned, natural gas boilers for space and water heating, and in apartment radiators for distribution. So if you go to the next slide. So the envelope retrofit is similar to what's being done in the Netherlands that Adam alluded to. The idea is to take a unitized prefabricated wall panel where windows are pre-integrated in the factory setting, and to essentially wrap the entire building in a new high-performance enclosure. In the rendering here, the roof is actually not showing panels, but there would be panels on the roof as well. The idea would be to take these panels and hang them off the existing structure if it's able to withstand the additional load, and then to wrap the underside of the second floor, so you get a new enclosure that is greatly reduced infiltration with high levels of insulation all the way around the conditioned space. So we're working with a panel manufacturer called Nexi that's actually based in Canada to develop this solution for the Eva White building. If you go to the next slide, this shows more of the building blocks of the envelope system. It's pretty similar to a SIP panel, but the skin on either side with Nexi's product is a proprietary cementitious material that gets adhered to an insulating core. And then the vertical and horizontal panel joints are sealed with a gasket, some compressible foam, and a few different layers of caulking. And then the panels bolt together with these steel corner blocks that you can see labeled in the image. Next slide, please. This is a cross-section view of the same building block. You can see here they're showing a reinforced edge that is thermally broken by the insulation. The insulation shown here is EPS. On the Eva White building, we're actually using a GPS to get another R1 per inch in the insulation to keep the total thickness down of the panel. And then you can also see some holes in the exterior of the insulation, and that's to allow for drainage should there be any issues with moisture penetrating the exterior facade. You can get the exterior finish in a variety of different looks, including kind of a brick veneer type look to preserve the the existing look of a lot of brick buildings throughout the Northeast. Next slide, please. On the mechanical side, this is actually a photo of the inspiration for the mechanical solution, which again comes from the Netherlands. This is a company over there called Factory Zero that makes these pre-integrated mechanical system pods that are prefabricated off-site and delivered to the building as a unitary package. And this shows the guts of one of those packages where they're lumping a heat pump for domestic hot water and space heating. There's not a lot of cooling needs in the Netherlands, which is an important difference from what we have here in the US. Domestic hot water storage tank, relatively small, an energy recovery ventilator, and then importantly, pre-integrated controls that allow both for comfort performance as well as remote
We're losing you.
Monitoring of system performance and fault diagnostics. So all that sort of comes in. Oh, can you hear me now? Hello.
Yes.
Hello.
Yep, we
Hopefully
can hear
folks
you.
can hear me. Okay, great. So next slide, please. Okay, thanks so much. Excellent. So applying this type of mechanical concept to a mid-rise building with a central plant presented some challenges, and we worked through a few different iterations of how we might implement one of these sort of per apartment systems in the Eva White building, and then eventually decided that all things considered, preserving the central plant was probably going to help reduce the upfront cost. And there was still an opportunity for sort of off-site prefabrication with the what we're calling the indoor pod, which basically consists of a fan coil unit or multiple fan coil units if it's a larger apartment, energy recovery ventilation, and then some controls that monitor temperature, humidity, CO2 levels, and can also provide for sort of demand response signals. And then we'd swap, the idea for Eva White would be to swap the central plant with and remove the boilers and put in an air to water heat pump or a VRF system. And then the real opportunity for integration between the mechanical system and the envelope is I think in this distribution piping. So for now, our original concept proposed running the new distribution lines, whether they be hydronic or refrigerant, between the new envelope panel and the existing facade. But I think in the future, there's a large opportunity for cost compression and streamlined installation if you could integrate these, the mechanical distribution into the panels themselves, such that when you hang the panels, the mechanical piping gets connected up, and then you just make the connections on either end in the unit and on the rooftop to complete the installation. Next slide, please. These are some early results from sort of the design concepts from our energy model of energy savings. And so you see the baseline case there, which has a alarmingly high 166 EUI. The next column over is the business as usual retrofit. This was the retrofit that was planned at the RAD conversion, which was largely an interior kitchen bath retrofit with some window replacements and lighting upgrades, which gets you about a 15% energy savings. We looked at an envelope only case where you're to preserve the existing mechanical system, but just retrofit the envelope, which gets you about a 53% energy savings. And then both of the realized packages, the hydronic rooftop plant and the VRF, got about a 77% energy savings. You can see the vast majority of savings are coming from reduced heating end use and water heating. And we're getting the big reduction in water heating is coming through the added efficiency of the heat pump equipment, as well as the opportunity for heat recovery during the summer months when the rooftop units are in cooling. Next slide, please. From an emissions perspective, we looked at the same set of cases, but we looked at a 2020 scenario and a 2035 scenario. Set of two bars represents in the graph. And in the 2035 scenario, we're assuming that Massachusetts reaches its renewable portfolio standard of roughly a 50% renewable grid by then. And so you can see, you know, one of the motivations for the all-electric retrofit is really the carbon reductions, the increased carbon reductions over time. That if the natural gas emissions are essentially locked in between 2020 and 2035, where you get this further reduction in the electricity emissions, such that with the realized packages by 2035, we're looking at about an 80% carbon reduction from the baseline case. And this is without considering any on-site renewable generation. Next slide, please. And then on the cost side, this graph shows the annual utility costs for a same set of scenarios. And while we are seeing, you know, around 77% energy savings and around the same opportunity for carbon savings, the annual utility cost savings are really only about 30% and being driven in large part by the opportunity for water savings. And this is driven mostly by the large delta in cost on a per BTU basis between gas and electricity. And so, you know, our great hosts at National Grid, I think, cut on either side of this coin, providing both. But I think this graph really highlights one of the challenges with the all-electric retrofit. While it's great from an energy and carbon perspective, that the operating costs are still an issue, which highlights the need for further cost compression of the upfront costs in this type of retrofit. So I'm going to pass it back to Adam now, and he's going to talk more about how we're thinking about scaling this type of retrofit approach to portfolios of buildings.
Yeah, I can see that thank you, Brett. I can see that we're tight for time. So next slide. Yeah, there you go. I can see that we're tight for time, so I'm going to give this a little short shrift, and hopefully people will be intrigued and will contact us when you see our contact information on the next slide, or our hosts will be kind enough to ask us back. The basic idea at the very highest level is to bring every piece of available information at a portfolio level to bear on understanding the physics of every building in the portfolio, generating a series of projects, more or less the scope that Brett laid out on the last couple of slides. Figure out the optimum times in each building's life cycle, major recapitalization events, major equipment replacements, times that are optimal for deep retrofits. Take all of that information and crunch it into a financing optimization engine, which locates the best time, the best year, say, to do the project, and also optimizes the financing product choices that are made, and then to lay those out on a calendar. As you can see, there are sort of fanciful Candyland version here. Each line is a property, all the lines are a portfolio, and you can then lay out the projects that make sense at times, and look for efficiencies in either spreading them out to maximize staff time or bundling them to maximize opportunities of developing projects together. So I'm going to leave it there. Next slide, please. If this intrigues you, there are the names, there are the email addresses, or just type RMI and Realize into a browser, and you'll pull up our team and a whole lots more information. Thanks. So let me hand it off to Meredith.
Great, thank you. You can go straight on to the next slide. I'm Meredith Elbaum. I'm the Executive Director at Built Environment Plus. You may formerly have known us as the U.S. Green Building Council Massachusetts chapter. We drive sustainable and regenerative design, construction, and operations of the built environment. What we do is we do a whole lot of education, some community building, a little bit of advocacy, like we're working on a zero net energy stretch code for Massachusetts. And then finally, we do some research. And this is, I'm going to be talking about a little bit of the research that we've done recently. Next slide. So I totally agree with our friends at RMI about existing buildings and the importance of existing buildings. And even thinking about that, any building that we build today that's a new building that's not built to net, that's not zero energy, is going to require more money to make it zero energy in the future. And so, you know, I have a picture of this soccer net. It's like we're scoring on our own goal. We're going in the opposite direction. So we need to do whatever we can to build. Every new building needs to get to be a zero energy building. Next slide. And I'm sure everyone's seen this slide tons of times. We know from our friends at New Buildings Institute that the number of zero energy buildings is growing exponentially every year. But I think we still have a question of, if that's the case, then why aren't we still having every single building that's being built today a zero energy building? Next slide. I think we're going to ask the question now, and we're going to ask a similar question as last time, but this is for all buildings, not retrofits.
Meredith, so far the responses are very similar to the last.
Not surprising.
We're having a little more uptick in the operator, occupant behavior, and trained workforce on this question than we did the last.
Okay.
All right, I'm going to go ahead and close the poll.
Great, so we can go on to the next slide. So in 2018, we held a municipal summit. We had 80 different representatives from municipalities across our Commonwealth, and asked them this question: what are your major obstacles to zero energy buildings? And just like you, these were the 5 different options that they came up with, and upfront cost was their #1 concern, hands down. And so moving on, so next slide, please. And that was what kind of got us started on this report called Zero Energy Buildings in Massachusetts, Saving Money from the Start. It's a report that was funded by the Barr Foundation that we worked with Integral Group on, and a whole bunch of our community members provided insight into this as well, including our friends on the line from BR+A. You can go on to the next slide. So we started by looking at studies that had already been done across the country on the cost premiums and upfront costs for zero energy buildings. Next slide. I mean, and I'll just say that there are many of those, and there's even more that have come out. Even recently, the city of Boston came out with their Department of Neighborhood Development a guidebook for zero emission buildings. It's not on here, but I highly recommend people go and take a look at that. It looks more specifically at the residential part of the cost for residential zero energy buildings and provides guidelines, recommendations for how we move forward in that front. Next slide. So we looked at a number of case studies. These are only 6 of the case studies that we looked at. We looked at a whole lot more and contacted the architects and engineers and owners to learn about these projects and what their characteristics were and to understand their upfront costs. That was the foundation for the study to start off. Next slide. And before I get into it, I want to just develop a common vocabulary with everyone on the call. Energy EUI, energy use intensity. I was joking with Jacob earlier that this is a phrase that 5 years ago, most architects and most people have no idea what it is. And if you said 100 EUI for an office building, people wouldn't know if that was good or bad. And in the past few years, it's starting to become a part of our common vocabulary, mostly in part due to the American Institute of Architects and the 2030 challenge and 2030 commitment. But so for the purpose of our study, we used site energy use intensity, which is all of the energy that the building uses divided by the gross building area, so energy use intensity. Next slide. And then I wanted to define, well, what do we mean by zero energy? There are lots of different definitions out there. There are different rating systems even between the International Living Future Institute, between LEED and others who have defined zero energy. For the purpose of this study, we broke it down into pieces where we start with what a typical energy use intensity would be for a building. We reduce that the energy through energy efficiency measures that are available and cost effective to get us to zero energy ready building. And for the majority of our the projects that we looked at and the projects that we modeled, we were able to reduce the energy use between around 45 to 50% with these energy efficiency measures. And so step 1 is to reduce energy use, and what we then call is a zero energy ready building. Next. Next slide. And once we have that zero energy building, that zero energy ready building, right, that has, for this example, it's a EUI energy use intensity of 13, we then need to levels to it. And on some types that we look able to have 100, or for some others, we could get partially renewable energy on site energy by purchasing all energy, and all that combined energy building. So
Meredith, we're losing your sound a bit.
okay, not sure what to do about that.
Sometimes if you slow down a little bit with the talking, it does help.
Okay, so if you can go to the next slide. Okay, so here, just to reiterate, and maybe if you couldn't hear me, we have a typical building, a residential building has an EUI of 27. We're going to apply the energy efficiency measures to that to get down to an energy use intensity of 13. We're then going to apply, and that gives us our zero energy ready project. We'll then apply renewables, either 100% on-site or a combination of on-site and off-site to give us our zero energy building. Next slide. So for this study, we looked at 6 building types, both existing office, the 10 buildings, K through 12 residential, multifamily, as a single family residential. You can go next, there you go. And so for each of these building types, ran an to how much could how and therefore renewable energy we would, so energy models, how much energy we could save, energy we would need for each of the building types. Next slide. I said before, energy efficiency measures that are readily available and cost effective across the envelope, the HVAC, water savings, lighting, and then also looking at the plug loads. Next slide. So, and then once we knew how low we could drive our energy loads and how much renewables we needed, we did a life cycle cost assessment. And you can see here that what we found was that for that upfront cost to get that building to be zero energy ready, we found that the zero energy ready cost, where we drove down energy as much as possible, could be anywhere from zero. It doesn't have to cost more energy and more money. And we did that through right sizing. You do that through orientation and through, if you can improve the amount, your envelope, so then your mechanical systems can get smaller. We found it doesn't have to cost more money to get to the zero energy ready building. But then we also found that, then there were some examples where it could go up to 7%. What we found was that it was a matter of design. And so for the case of the study, we focused on, and what I'm going to show you coming up is the assumption of the 5% for the ready. Again, it actually, of course, the lower up your zero energy ready costs are, the more affordable the entire. And the cost of the renewables for both on and off, what would be our energy savings, which would then give us our break-even year and the dollars saved. Next slide, please. So I'm just going to show you one example of the 6 building types. This is all available on our website. But this is the K through 12 schools, and you can see in the figure on the left that we are able to reduce our energy use by 44%, and it went to a 100% electric building. And then on the right, you can see that we then were able to offset 100% of the energy on site with PVs. Next slide, please. And I just wanted to point this out. This isn't the case for every building type. And the previous presenters mentioned this a little bit. One of the issues right now is that electricity costs so much more than gas. And people are worried about adding capacity to the electrical grid. And that's where energy efficiency plays such a huge part in what we're doing. And so if you look here, through those energy efficiency measures, by saving 44% of overall energy, even though we went to 100% electric, our overall electricity alone is still less than the baseline building. right? And so this is an example of a building that would not add a zero net energy building that would not add greater capacity to the electrical grid. Quite the opposite, it would actually take energy, it would be less energy than was on the grid. And of course, we've actually offset it with PV. Next slide, please. And then for each of these, we looked at, so we have this for each of the projects. This is showing the cumulative annual expenditure, comparing the two, and you can see here that at about 15 years, it's break even, for schools, that are gonna be around for hopefully over 50 to 100 years. That's relatively fast. Of course, this is assuming the 5% premium for the zero energy ready. And that doesn't have to be, it could be much less than that. Next slide. It's another way to show that, looking at the annual cost difference, and that we ended up with 4.8% savings in cost. Next slide, please. And this is going back, looking at the payback periods for different first cost premiums, right? If you look at for all of the building types, so this is really the summary of the entire study, looking at that first premium just to get to zero energy and what it would cost to then make it to make it zero energy ready, and then the cost to make it a zero energy building. Jacob likes to remind me that this slide is really showing, or the assumption here is that the building owns the photovoltaics. You could do a power purchase agreement, and at that point, you wouldn't be paying money up front at all for the on-site renewables. And so you can see here for existing office buildings, and I also want to point out for the existing office building, the baseline is that you're doing a full building, that you're doing a full renovation of the building. The baseline is not doing nothing. It is, the comparison is to if you were renovating the building and up to code versus renovating it to zero energy. And so next slide. And the cost premiums, right? It can be as low as 2%. It does not have to be high. It could even be down to zero. So next slide. Looking at the time. Next slide. There you go. So just a couple examples. Oops, back one. Okay, two last examples from me, and then I'm going to pass it to Jacob, which is that here's a school in Cambridge, Massachusetts. This is not a zero energy school, but it's pretty darn close. Its energy use intensity aligns directly with our studies, as does actually the cost per square foot of our baseline. And so proving that this does not have to cost more than an average school. One interesting thing about this is that the school did retro commissioning and were able to reduce their energy use by 30% through retro commissioning, pointing out the importance of doing retro commissioning on these projects. Next slide. We saw this on the National Grid opening slide, the King Open School, also in Cambridge, Massachusetts. And one of the things I like to talk about this project is, if you look down there at the occupant engagement, that it's my understanding that how do you get these buildings so that it doesn't cost any more? One way, at the onset of this project, they realized that all of the existing classrooms had microwaves and refrigerators and hot pads for the teachers because the break rooms were so far away. And so in the new building, they made sure to have accessible break rooms for all of the teachers so that they could get all of those plug loads out of the classrooms and consolidate them. And so a huge amount, they had a high percentage of energy savings was just through the smart design of the building. Now I'm going to pass it on to Jacob to talk about a couple more of the case studies that we presented in the study.
Next slide. Chelsea Soldiers Home is a 250,000 square foot inpatient healthcare facility. It's for veterans, targeting an EUI of 66. It is in construction right now. The entire geothermal bore field has been drilled. Next slide. And the construction cost premium was less than 1%. It was actually 0.2% premium to achieve net zero. Next slide. BU Center for Computing and Data Sciences. This is a 350,000 square foot, 20-story high-rise in construction right now in Boston. Similar to Chelsea, the entire bore field has been drilled. It uses 31 boreholes. Each borehole is 1,500 feet deep. It uses a concentric pipe within a pipe system to handle the pressure in that kind of configuration. And we're targeting a 40 EUI for a building that runs from 5 a.m. to 11 p.m. And go to the next slide. Similarly, we achieved less than 1% cost premium compared to a conventional design to achieve a net zero building. Next slide. And Bristol Community College, we're going to dive deeper into this as a case study momentarily. So Meredith, do you want to wrap us up on the last slide?
Meredith, you're muted.
Oh, I couldn't unmute. Okay, unmuted. The last slide is that you can find our report on our website. I encourage you to go take a look at it. And I also just wanted to let you know that if you want to dive deeper into some of these strategies used on these projects, we're having a building tech forum 4 to 6 p.m. tomorrow. You can find it on that same website, builtenvironmentplus.org. Thank you.
Do we want to, okay, there we go. So what do you think is the cost premium for a net zero laboratory building compared to a conventional design? What would be the premium for cost? You can go ahead and punch in your response.
Okay, well, the fight is on for 0 to 4% versus 5 to 9%. I'm going to go ahead and close out of this poll. Everybody get a last chance to go ahead and vote. Okay, it looks like our response is 5 to 9%. Jacob.
All right, so we'll see where we end up. We've got this case study to illustrate one example of the cost premium. So this is Bristol Community College, Sprague Building for Health and Science. It is a 50,000 square foot medical, dental, chemistry, and biology teaching facility. Go ahead. Next slide. There we go. You can see the campus here. The building is in red. Next slide. And the first floor has the dental clinic and medical teaching facilities. Next slide. Next slide. Next slide. And the second floor has all of the biology and chemistry wet labs and support spaces. Next slide. Great. So the project started out about 8 years ago as a conventional high performance design meeting LEED Silver Plus to Massachusetts state funded project standards, which means it had to be 20% better than the baseline at the time. But it still was using all conventional systems, including natural gas consumption. Next slide. The project then went on hold, awaiting approval and funding from the state. And a year later, it came back to life. Next slide. And the college had doubled down on their commitment to achieving carbon neutral by 2050. Next slide. Part of that commitment was they were negotiating a power purchase agreement to install a 3.2 megawatt solar array over the parking lot directly adjacent to our new building would be built. Next slide. So we did an energy model of our building thinking, hey, we've got this great LEED silver design, should fit nicely with their new solar panels, and we're off to the races. So when we did the energy model, next slide, it showed that you would use about half of that entire 3.2 megawatt array. Next slide. And about 120 homes worth of natural gas. So clearly that was not going to meet their goal. Next slide. So the question was, how do we do better? Next slide. And so we put together a package of strategies that we felt would best meet the carbon neutral goal. We're going to go through each of those very, very quickly. Next slide. Tony?
Sure. Thank you, Jacob. As the mechanical engineer, I believe the heart and soul of this Braga building was a prefabricated heating and cooling plant. The plant had 3 geothermal water source heat pumps, 3 hot water heating loops, chilled water coils, all the VFDs, water piping, power and controls were built in a clean temperature controlled facility offsite. The plant was fully commissioned prior to delivery and installation into the building. Next slide, please. Big piece of how we get to net zero, we replaced all the ducted fume hoods with filtered fume hoods, significantly reducing the size of all of our air handling equipment, including 100% outside air handling units, our exhaust air system, and all associated ductwork. An air quality monitoring system, air acuity, continuously monitors room VOC levels, increasing and decreasing ventilation and exhaust air as needed. Next slide, please. 100% outside air handling units were equipped with enthalpy heat wheels, providing ventilation to the building occupants. Fan cooling units provide room heating and cooling. The systems are completely decoupled from one another. When the building is unoccupied, the air handling units run at minimum set point. When the rooms are unoccupied, all the fan cooling units are off. Next slide, please.
We also addressed the lighting power density. We were able to achieve a 0.5 watts per square foot in the lab spaces. Next slide. And we did a detailed plug load study to right size the systems, which significantly reduced the mechanical cooling loads. Next slide. Now, normally for a lab building, the envelope is not a big driver, but once we reduced all of the other loads so dramatically, it actually became important for us to enhance the envelope and at least meet the code requirements for both the mass and stud wall assemblies. Many buildings, particularly back 6-7 years ago when this was in design, did not carefully address things like thermal bridging, and we made sure to do so. Next slide. There was a lot of care taken during construction too to make sure there's an airtight envelope, and when the blower door test was performed, next slide, we achieved roughly in the range of passive house level of performance, far outperforming the specified requirements for the project. Next slide. We also have natural ventilation, both manual in the individual spaces and a fully automated system in the main atrium space. Next slide. You can see the weather station on the roof in the next slide and the airflow pattern using both wind direction and buoyancy. Next slide. Ultimately, we reduced the energy consumption of the proposed design by 70% compared to the original solution and essentially eliminated natural gas consumption. Next slide. The real question was, can we afford it? And so I mentioned earlier, this project started out as a conventional project and was fully approved and funded on that original basis of design. So when we said to the state, hey, the college wants to achieve net zero, we have to change our design, they said, no way, it's been already approved. We said, well, give us a shot. We'll design both the original design and the net zero design on our own dime through schematic design. And if we prove that the net zero design can fit within the budget, state should say yes. And the state, of course, wanting to achieve carbon neutral, said, okay, we'll take your bet. Next slide. The original cost estimate came in showing that it was essentially cost neutral. We then validated that with the final construction costs, and it ended up being about a 1% construction cost premium to achieve net zero. So for all of you that guessed between 0 and 4%, good job. Absolutely achievable, even for a lab building. Next slide. We also were awarded a Pathways to Zero grant and utility incentives that more than covered that 1% premium and allowed us to add a fair amount of metering and monitoring that allows us to monitor how the building's working and make it a case study as we see today. During the operation of the building, you see there's a significant amount of savings, both from the building operation and from the fact that the PPA provides lower electric costs than it would have been to procure that energy from the grid. That's equivalent to this tuition for 50 students every year. Being a community college, that's really critical for their bottom line to be able to serve their community. So this is beyond sustainability for the environment. This is sustainability for their service to the community. Go ahead. We've since been monitoring the energy consumption, next slide, and we have hit our target of 45 to 50 EUI per year, which is shockingly low for a lab building in a cold climate. Next slide. And this is the, on the left, the hourly energy production in green versus building energy consumption in blue. On the right is the total annual. And this really illustrates to me the drive and the need for energy storage in batteries to be able to manage these, just the disparity between the high solar production during the peak daytime and the building needs that are much more continuous. And that's the end. Thank you.
Great. We just have a couple minutes left. Thank you for your presentations, panelists. Those were fantastic. My first question here is for Adam and Brett. Are deep retrofits at scale prohibitively expensive for New England's old building stock?
I think the answer is, I think we have to define the word prohibitively. Under current volumes of supply and current levels of demand, there is a significant gap in the viability of an immediate net zero project today. That's why we're in a piloting phase to pilot the technologies. What the work in the Netherlands showed is that if you scale demand up to several thousand units a year, that price point comes down significantly for both the panels and the mechanical pods, and then you can achieve a retrofit which is which you can pay for through underwriting the savings. So the question is a chicken and egg problem of how do we get from here to there, and we'd be happy as a follow-up, Brett and me, to point you towards that those real results in Europe and how we're planning, working with NYSERDA, California Energy Commission, and DOE, in order to bring that price compression, cost compression down in the US so that we have viable retrofits.
Great, thank you. And a question for Tony, just to wrap up. After we get Tony's answer, we'll probably be logging off here. And I just want to let everybody know whose questions hadn't been answered or had specific questions to the National Grid team. We'll be passing those along and following up individually where is necessary. So Tony, for our last question today, what is the most commonly seen design obstacle that makes it difficult to meet net zero?
Sure, thank you. I think the biggest obstacle is probably the implementation of new technology for the building owners. A lot of things we're bringing to them they may not have seen before. They may not have them on campus. So there's a big educational piece that our architects and engineers have to teach the owners what they're going to have for systems and learn how to maintain what we've designed and built. Jacob, anything to add?
No, that's great.
Great. Well, you guys did a great job. Thank you so much. Thank you to our attendees today. Don't forget, we have policy webinar coming up on June 2nd. The information is there on your screen. You can also find a link to register on NBI's event website. Laura, Mona, anything to say as we close today?
I'd just like to say thank you everyone for joining, and we look forward to seeing you at the next webinar. And thank you to all the panelists. Have a good afternoon.
Thank you.